Hi, my name is Ching and welcome back to Data Structures in C++. In the previous lecture, we talked about singly linked lists and their advantages compared to arrays. But singly linked lists have their own limitations. For example, they cannot describe rotating scenarios, and it can only traverse in one direction. To overcome those limitations, we'll talk about some other kinds of linked lists. Specifically, we're going to talk about circular linked lists, doubly linked lists, and doubly circular linked lists. In addition, we can also design application-specific linked lists to solve specific problems, such as the linked lists for polynomials and sparse matrices. First, let's introduce circular linked lists. They're very similar to singly linked lists, but the last node points to the first node. Instead of maintaining a head pointer, circular linked lists usually maintain a tail pointer, which keeps track of the last node in the list. The tail pointer is just one step away from the head pointer, so we only need to maintain the tail pointer for the whole list. The nodes in circular linked lists are often sorted, and we will use that in our examples. Here are the core operations of circular linked lists. They are very similar to the singly linked lists. We will implement the insert, delete, and traverse operations. Let's first start from the insert node function. Because of their circular shape, there are only two scenarios we need to consider: the insert to an empty list or a non-empty list. Let's talk about the empty list first. First, we create a new node which we're going to insert into the linked lists. Second, because this is the only node in the list, it is also the tail. Therefore, we assign the new node to tail. Last of all, we close the circle by assigning this tail's next pointer to itself. Now, if the circular linked list is not empty, because it is circular, we can think the insertion always happens in the middle. First, we find the two nodes where we want to insert the new node. We call those two nodes the predecessor and the successor. Second, we insert the new node in between the predecessor and successor by updating the pointers between them. So the predecessor is pointing to the new node, and the new node is pointing to the successor. The special case here is when the new node is added to the end of the list, so that it becomes the new tail. Here's the sample code for the insert node function. We pass in the tail pointer as a reference, because the function may need to update it. First, we have the code for the empty list scenario. Second, we find the predecessor and the successor, assuming we maintain a sorted list. Here are the actual insert operations. Last of all, we update the tail if necessary. The delete node function is just the opposite of the insert node function. There are also two scenarios. If there's only one node in the linked lists, or we are deleting a node in the middle of the list. Let's look at the first scenario. First, the tail will become an empty pointer. Second, we destroy the current node. Now, let's try to delete a node from the middle of the list. First, we find the predecessor. Second, we connect the predecessor to the successor of the current node. Third, we destroy the current node. Last of all, we update the tail if necessary. This results in the current node being deleted from the middle of the list. Now let's look at the code. First, we find the predecessor and the current node with the given value from the parameter. Second, we handle the single node deletion. Third, we update the tail if we are going to delete the last node in the list. Fourth, we connect the predecessor with the successor. Last of all, we destroy the current node. Traversing is almost the same as in singly linked lists. The only difference is, now we don't have a head pointer, but we can get the first node from the tail pointer with just one step. Then we follow the list until we hit the tail. So far, we extended from singly linked lists to circular linked lists, but we can only move in one direction along the list. What if we want to move in two directions? Let's introduce doubly linked lists. Doubly linked lists are similar to singly linked lists, except every node has a previous pointer and a tail pointer, so that each node can easily access both its successor and predecessor in constant time. To have quick access either from front or the end of the list, we maintain both the head and tail pointers. Let's take a look at the insert function. In this case, we insert after the node with value 20 in the list. So the new node's predecessor and successor have value 20 and 30, respectively. First, we connect the new node with its successor. Second, we connect the new node with its predecessor. Third, we assign the new node as its successor's predecessor. Finally, we assign the new node as its predecessor's successor. Now, we'll talk about deleting a node in the circular linked lists. We only need 3 steps. First, we connect the current node's predecessor to its successor. Second, we connect current node's successor to its predecessor. Last of all, we delete the current node. What if we combine the benefits of circular linked lists and doubly linked lists together? That will give us the doubly circular linked list. Doubly circular linked lists are doubly linked lists, except the head in the linked list becomes the tail's successor, and the tail becomes the head's predecessor. Therefore, there are 2 circles in this linked list. Similar to circular linked lists, we only need to maintain a tail pointer. Now let's talk about some applications for our linked lists. First, we can use singly linked lists to implement both stacks and queues easily, as we had mentioned in the previous lectures. For stacks, we can simply push and pop from the front. For queues, if we maintain an additional tail pointer, then we can enqueue to the end and dequeue from the front. All of those operations run in constant time. Sometimes we can design a custom linked list for a specific problem. For example, we can extend the singly linked list to represent a polynomial. In this linked list, we will have 2 variables to store data, with one for the coefficient, the other for the power of x. So let's look at this polynomial. We create the first node from the first term from the polynomial. In this case, the coefficient is 4 and the power is 31. Then we create the second node from the second term, and so on. Therefore, we create a compact representation of polynomials. Similar to polynomials, we can use linked lists to represent sparse matrices efficiently. Let's see what sparse matrices look like. Sparse matrices are matrices where most of the elements are 0, and our goal is to only store those non-zero elements. Here we have a sparse matrix that contains 5 non-zero values. Now let's see how to design a linked list to store that sparse data. First, we will have the head node to describe the information of the matrix, such as number of rows, number of columns, and how many non-zero values. Then we will start with the first row, which contains at least one non-zero element. In the matrix, The first row has 2 as the non-zero value, and it is at the column index 3. We continue this linked list for the next row. In this case, it is the row at index 1. This row contains 2 non-zero elements, which are the value 1 at the column 2 and the value 5 at the column 5. Those 2 nodes are linked together in the order from left to right. We continue for all rows and skip the empty rows. Now we have a compact representation of a sparse matrix. In summary, we learned that singly linked lists can be extended to multiple types of linked lists, such as circular linked lists, doubly linked lists, doubly circular linked lists, and other variations. All of them were designed to efficiently manage a list of data. Last of all, we used a few examples to show the applications of linked lists. It can easily implement stacks and queues and be used as a compact way to represent sparse data. This concludes today's lecture. Have fun and happy coding. I'll see you next time. Bye.